Central force is the most important force which helps to solve Kepler's problem in classical mechanics. In this video, let us seek the assistance of central force to deduce Kepler's second law of planetary motion, which is also called as law of areas. Let us consider a particle of mass which is moving about a fixed center O. For such a particle moving under a central force, by the definition of central force, the force F is defined by F of r, small f of r into r vector by r. This f of r is nothing but it is the function of distance r. Here the f of r is nothing but it is equal to minus dou v by dou r into r vector by r. Here this capital V is nothing but that is the potential energy of the system. Next, let us write the Lagrangian function for this system in polar coordinates. We all know the polar coordinates are represented by r, theta and phi. Again, by the definition of central force, any particle which moves under a central force, the movement is confined to a plane only. So, only two coordinates will be involved. That means r and theta, and here the phi is the redundant coordinate. So, phi is not involved here. The kinetic energy for this system is given by, or in terms of the polar coordinates is given by, T is equal to half into m into r dot square plus r square into theta dot square. We are much familiar with this equation. I am not going to give much importance to this. In many problems involving polar coordinates, we might have used this, the kinetic energy of the system, as T is equal to half into m into r dot square plus r square theta dot square. We all know the Lagrangian function L is equal to T minus V. T is the kinetic energy, V is the potential energy. So, we have both the kinetic energy of the system and the potential energy of the system, and let us substitute it. We get L is equal to half m into r dot square plus r square theta dot square minus the potential energy V of r. So, looking at the Lagrangian function, we could see that theta do not appear in the equation of the Lagrangian function. So, look at the equation 3, which represents the Lagrangian function. In that we could see r dot and theta does not appear in equation 3, which means the Lagrangian function is independent of theta, or theta is an ignorant coordinate or a cyclic coordinate. So, we can write dou L by dou theta is equal to 0. So, next let us find the conjugate momenta or canonical momenta corresponding to the coordinate theta, that is the p theta equal to dou L by dou theta dot. So, let us differentiate this Lagrangian function L with respect to theta dot. So, the first we have three terms in equation 3. So, the first term is half m into r dot square. So, that term does not involve theta dot. So, it is half into m into 0 plus half into m into r square. In equations 3, you can see in the second term we have a theta dot. So, dou L by dou theta dot, since it is a theta dot, we have to differentiate it. So, differentiating we get 2 into theta dot. The third term is minus V of r. Since it do not involve theta dot, we are not differentiating. So, we are left with m r square theta dot. So 2 and 2 will get cancelled. We are left with m r square theta dot, just represented as equation 5 here. This again, by the definition of central force, this m r square theta dot is nothing but it is the angular momentum of a particle moving under the central force. Next, let us write Lagrangian equation of motion in terms of theta. If you write the Lagrangian equation of motion in terms of a cyclic coordinate, we may solve the problem very easily. Since certain terms will be zero, the terms which we have to deal with becomes a less. So d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. Since theta is a cyclic coordinate, dou L by dou theta is equal to 0. We have only one term. So dou L by dou theta dot, which is equal to mr square theta dot. Let us substitute in it. We get d by dt of mr square theta dot, which is equal to 0. So when we integrate this equation 6, we get mr square theta dot, which is nothing but the angular momentum. Now we are going to represent it by capital J, which is a constant. We all know the angular momentum of a particle moving under a central force is a constant. This is again proved here by equation number 7. This equation 7 is also called as the first integral of motion. We have another equation, second integral of motion, which we will see in some other video. Here, this 7 is called as the first integral of motion, again which implies the angular momentum J is a conserved quantity. Okay, so again let us go to equation number 6, d by dt of mr square theta dot. We know mass is a constant, we can take it outside, and half is also added here. We have this half factor to make that term as half r square theta dot, which is nothing but the aerial velocity of the particle or the system. This is nothing but the area covered by the particle by the radius vector per unit time. So this half r square theta dot, generally called as the aerial velocity, is nothing but it is the area swept by the radius vector per second. The differential area swept out in time dt, that is dA by dt, is, first let us find out what is dA. dA is equal to half into r d theta. So which gives out half into r square d theta. So dA by dt becomes half into r square d theta by dt. So d theta by dt is nothing but it is theta dot. So half r square theta dot, which is the aerial velocity by. So here we have found this half r square theta dot is a constant. Hence the motion of the particle taking place under a central force, the aerial velocity is a constant. This is in accordance with the Kepler's law of areas. Hence, central force problem helps in deducing Kepler's second law of planetary motion, which can be stated as the radius vector drawn from the sun to any planet sweeps out equal areas in equal times. This equal areas in equal time is nothing but the aerial velocity of the